Okay, let's trace the absolutely incredible physical journey of electricity. In this explainer, we're going to start from the exact moment it's generated, follow it across vast, sweeping distances, and finally reveal the highly complex, specialized engineering maps that actually keep this entire system from just collapsing. So think about the specific device you're watching this on right now. How exactly does a spinning turbine, maybe hundreds of miles away, manage to seamlessly power that screen without a single interruption? Well, the answer lies in this massive, invisible architecture that surrounds us every single day. At its very core, a power system is essentially a colossal, interconnected network. You can really think of it as the ultimate bridge. On one side, you have your raw energy sources, right? Things like coal, wind, solar, or nuclear. And on the exact opposite end, you have the end user's appliances or heavy industrial machinery. The grid is that critical, life-giving link in between. And the sheer scale and variety of physical components required to make this energy bridge actually work, it's just mind-blowing. We are not just talking about a few wires strung up on poles here. This network relies on massive synchronous generators, step-up and step-down transformers, incredibly long transmission lines, heavy switchgear, highly sensitive protection relays, and of course, the electrical loads themselves. Every single piece of this puzzle has to operate in perfect harmony. Now, to actually make sense of all this complexity, engineers logically break the journey of electricity down into three highly specific physical stages. First up is generation, which is converting mechanical energy into electrical energy. Second is transmission, the bulk transit of all that power over really long distances. And third is distribution, which is the localized delivery directly to consumers. All right, kicking things off with generation. When electricity is initially created, it's typically generated at standard ratings somewhere between 11 and 25 kilovolts. Now, I know that sounds like a massive number, but in grid terms, it's actually kept relatively low. This specific limit exists because of the strict insulation limitations of the generator stators themselves. You simply can't generate power at 1,000,000 volts right out of the gate without completely destroying the equipment. But here's the catch. For long-distance primary transmission, moving this power across entire states or vast regions, that starting voltage has to be massively stepped up. Using transformers, the grid pushes this voltage from 11 or 25 kilovolts up to 220, 400, or even an astonishing 765 kilovolts for primary transmission. You might be wondering, why on earth step it up that incredibly high? Well, it literally boils down to pure physics. Higher voltages mean lower current for the exact same amount of power. By dropping the current, you drastically reduce what are known as I²R heat losses. This is absolutely crucial because it prevents those cables from literally melting as they carry power across vast interstate distances. Now, obviously, you can't just plug your television into a 765 kilovolt transmission line. No way. So as the power finally approaches your neighborhood, it enters the distribution stage. It's carefully stepped down through secondary transmission to 132 or 66 kilovolts. Then, local substations drop it further to 33 or 11 kilovolts for industrial consumers. Finally, street-level transformers step it down one last time to a usable 415 volts for commercial loads, or the nice, safe 240 volts your home appliances actually require. But all of this sheer volume of infrastructure creates a massive challenge for the people running it. In physical reality, a three-phase power grid is, well, honestly, it's a wild, cluttered maze of wiring. Engineers can't just go out and look at a physical grid to diagnose problems or plan expansions. It's way too tangled. So to strip away all this visual clutter, they rely on these elegant, streamlined maps known as SLDs. Enter the SLD, or single line diagram. This is a brilliant, simplified standard notation. Instead of drawing out all three physical electrical lines for the three phases, actually scratch that, drawing all three would be a total nightmare. Engineers just use one single line to represent the entire circuit. They place standardized symbols along this line for generators, transformers, circuit breakers, and complex flow control equipment like fax devices. It creates this beautifully clean, readable map of the whole system. But don't get me wrong, an SLD is way more than just a pretty map. Without this elegant single-line simplification, engineers literally couldn't perform the critical mathematical analyses required to keep the grid perfectly balanced. SLDs are the absolute foundation for conducting load flow studies, executing short-circuit analysis, and coordinating protective relays, which is what ensures that a single fault in one neighborhood doesn't suddenly black out your entire city. So, to actually manage these SLDs and run all those intense calculations, engineers rely on a very specific digital toolkit. We can broadly divide this software into two main buckets: programs used for complex dynamic simulation and tools designed for precise 2D drafting. Diving into the simulation side, ETAP is definitely the heavy hitter. It stands out as the industry standard for comprehensive system analysis. What makes ETAP so incredibly powerful is that it lets engineers visually model the network and then immediately run those critical load flow, short circuit, and motor starting analyses directly from the single-line diagram they just built. It's a real game changer. But, sometimes engineers need highly specific dynamic testing. Say they're building custom control blocks, they turn to MATLAB and Simulink. Or if they are running electromagnetic transient studies, like testing specialized protection relays and flow control devices, they use PSCAD. And for grid operators looking at massive, wide-area power stability and harmonics, Die-Silent Power Factory is their go-to tool. Then, on the flip side, you have your 2D drafting tools, programs like AutoCAD Electrical and ePlan Electric P8. What's kind of fascinating about these is they don't actually simulate power flow at all. Instead, they provide the strict, industry-compliant standards for precise visual design. We're talking about laying out everything from your standard 2D single-line diagrams to incredibly detailed, automated, database-driven machine wiring. So we've traced this raw energy from spinning stators up to astonishing 765 kilovolt transmission lines and all the way back down to the safe 240 volts running your home. The very next time you plug a device into the wall, what are you going to picture? That massive physical journey traversing the countryside, or the elegant single-line digital maps and complex simulation software keeping all of that immense physical chaos under perfect silent control right inside your walls? Something to think about. Thanks so much for joining me on this explainer, and keep learning.